when I asked what the brief was, it was sort of, well, kind of round it off. And should I be controversial? Oh, go on then. So I thought, how can I be controversial? I thought, Room 101. I've had a list over the years of things that I wanted to put in Room 101, but I've never actually vocalized them. And I think it started in Radio 5, actually, Room 101, didn't it? The concept of things that you don't like, putting them into a room and you never have to see them again. So I've got a list of about 3, and I'm going to work through them. And I've also given myself a challenge here to use the word metaphor, uncertainty, 100 years, and Baroness Thatcher. So I haven't really got a clue. I'm going to weave them in, but I'll do my absolute best. Yes, there's York. Where's the keyboard? Oh, how'd you get it? Oh dear. I've got it. What day is it? Yeah, there's a wonderful picture of York University in its context. It's a great city to work in, a great city to live in. And I've been here now for 12 years. And I really, one of the reasons for coming here was the opportunity to work with other disciplines. In particular, there's an organisation called the Stockholm Environment Institute, which is well over 20 years old. And there's a metaphor. Got a metaphor. Here's a metaphor for the way that everybody was going at the end of the 1980s. And there's a metaphor of a lone cyclist heading in the opposite path. And that was really what SEI was doing. They decided that they really should be bringing together science and policy, and that science should be informing policy, and policy should be in some way directing the science. And it's gone on from strength to strength. So I think it was proven to be right. And the most interesting, well, not the most interesting, but a very nice part about that is that now SEI is ranked as the 6th most influential environmental think tank in the world, which is quite impressive when you think about its origins and how big the world is. Right. That's how big the world is. Now, I want to get in hope as well, which I can only do it temporarily. Let's look at this. I give you hope. I give you hope. I'll tell you why I give you hope. Well, first, you look at this and you think, that's quite depressing. These 3 gases marching relentlessly upwards, and it's going to cause problems. And that's a problem that we have to deal with. We've got to find mechanisms, ways around this. But I would suggest the hope is even stronger. The hope, really, the positive part, is that we spotted it. We know it's happening. It's invisible gases that we cannot see. We're not sure where they're coming from, where they go to, whatever, but we spotted there's a problem. We spotted the ozone hole, and we did something about it. The great Satan metaphor, the great Satan is if we're ignorant. That's the real problem. If we don't know about these things. So there are things lurking out there, potentially, which could be far more worrying than these, and more worrying than the ozone hole, that we have to keep our eyes open for and to look out for. And that involves measurements. That involves people going out and measuring things. Now, Room 101. Are you all familiar with the concept? Yes? What about the Americans? Is an American left? Any idea?
I have no idea.
Okay. 1984, yeah. It's this is the place where if you want to, let's say you have that relative that you can't stand and you wish you'd never see them again. Room 101 is the place for them.
I just moved to a different continent.
Maybe you're in room 101. I don't know. So the concept is I'm going to build up some kind of fervour towards things that I would like to see put into room 101, and I think I'd like to take you with me if I can, but I don't know whether you will. At this point, it's probably wise that if you've got to leave to catch a train, if in some way you go T on the way out through the door so that no, you had to leave, whereas if you've actually been offended, if you could do a different O shape or something, you've left in disgust. Because I'm hoping not to identify too many individuals. Here's my first exposure to global or national maps, the synthesis of information for policymakers at a scale which is relevant to somebody who might have a constituency. And I looked at these maps and I thought, wow, brilliant, they're fantastic. In fact, I helped contribute towards their construction. And here's a map of the amount of carbon in the UK in the vegetation, and there's a map of the amount of carbon in the soil in the UK. And I thought, we created these maps, and I thought, what are they there for? And I think they've just been created to taunt the French, I'm not sure. But this is... Look how we go. Well, it only takes 5 minutes for a soil scientist to look at this map to realise, well, actually, the Scottish Soil Survey system, they did everything to a metre depth, and we, in the south of the border, did everything to 30 centimetres. So there's a real flaw in the map for us now. But at the same time, I was working at a place called Morehouse. Now, Morehouse, only one person's mentioned the IBP, and I think the IBP was an incredibly wonderful thing. It was the International Biological Programme where people actually went out and measured things. They measured primary productivity, they measured nitrogen, they measured all kinds of things at certain sites very intensively. And we're still using those data in a lot of our current evaluations. In fact, you see in the IPCC reports, you still see the harmonic of data collected under IBP. It's also an NERC Environmental Change Network site. And I was working there extensively, and I thought, hang on a second, I've just been told from that national map how much carbon there is in the vegetation and soils of this region, and we were also working on that. So what we decided to do, we thought we'll mark out 20-odd square kilometres within the Morehouse National Nature Reserve, and we just so happened to have this rich legacy of plant distribution, of soil sampling. The site was intensively studied in the 60s, and so we used the data, and we took some new measurements, and we decided we'd establish in these kilometre squares how much carbon we had in the vegetation and in the soil. And here we go. There's the vegetation map. So that is a detailed vegetation map of Morehouse. I haven't given the classification. We knew exactly how much carbon was in every one of those vegetation types because they've been sampled by people like John Grace and a whole host of foolish ecologists. So we're able to calculate the amount of carbon at the site. We had really very detailed, because of a guy called Mike Hornung, I think, largely, detailed soil maps of Morehouse, and we had analyses of the different soil types. So similarly, we could create a map of the soil carbon at Morehouse. And then you do the rather foolish thing of saying, well, this is the number in the national database, or these are the numbers, and this is the truth. I mean, I say truth. This is as good as I can get. Let's put it that way. You probably, if you went down to square centimetres, you could get to the total number of carbon molecules, but they wouldn't be there anymore. So I began to question these maps, and I thought, well, you know, I don't like the maps. I like the maps because I like to look at them. A map like that, it carries an incredibly important concept, and it communicated a very important concept to government at the time. It said, most of the carbon is not sitting in your vegetation. If you look at the scales here, 1 kilogram carbon per metre squared max here, it's sitting in the soil. So if you want to protect or enhance carbon stocks in the natural environment in the UK, you need to be looking after your soils. And it actually affected the policy on whether we would be ploughing up peats in order to plant trees to sequester more carbon into the vegetation. So the concepts that came across from these maps, quite important. But actually, if you look at under every pixel, you start to get worried. Here's a collection of pixels for you, a paper that was published in Nature a couple of years ago, which shows the global estimates for methane emissions from wetlands. Now, wetlands are the largest single contributor to methane fluxes into the atmosphere, so these wetlands are incredibly important with regard to the global balance. And this diagram appeared one day in the pages of Nature, and I was a bit taken aback because I thought, hang on a minute, why am I bothering going there every couple of weeks with my systems for measuring methane fluxes if we already know what they are? Because it's just been published in the page of Science. So this landscape, quite honestly, 6 years ago, I looked across that landscape and I said, I haven't got a clue whether this is a net source or sink of methane. And I've measured methane emissions quite a number of times over the years, and I just couldn't tell you whether it was a net sink or a net source. But that paper told me, rather reassuring, and I was quite concerned about the mismatch between people on the ground taking the measurements and these maps and these models which are being generated. It's a complicated process, methane production. It's a net The net flux that comes into the atmosphere is a mixture of uptake and emission. And as you go around a site, you can measure places that are taking up methane, you can measure places that are emitting methane, and then you can try and draw an overall budget. You can use different scales of resolution, and at this particular site in Wales, in Lake Vyrnwy, we used everything ranging from good old manual cover boxes through to eddy flux systems and an eddy system on an aircraft. So it's possible to use different scales of measurements to get to these fluxes. And so what we did is we partitioned the vegetation to various types, and then we got victims, including myself, to go out and measure methane fluxes at regular intervals, get very, very wet and very cold, and come up with figures. And then we started to compare the figures with literature and IPCC estimates and so forth, and discovered, in actual fact, that the IPCC estimate for systems like this is based upon a number of studies that were done partially throughout years. The complete year of study was rarely ever done. And as we dug deeper and deeper into the references, we realized there was a reference by a chap called Dickie Climo from, I think it was 1978, and he's the only person who'd actually taken an annual series of measurements of methane fluxes of a wetland system in the UK. And yet this figure has propagated itself up to the IPCC assessment. And when we contacted Dickie and said, we can't get hold of the original paper, could you send us one? He said, why? And we said, because it's the foundation of an estimate in the IPCC. Ooh. And there was a kind of, has nobody been out there since? Incredible. So here we are, we've got some methane measurements. Let's scale it up. Let's scale it up for this area and then compare it to that global estimate that's been produced. So we know the different vegetation types, we classify them, we know how much methane they're producing, we can multiply the area by the flux. We can come to an estimate, and I'm pretty convinced that, I'm not going into detail, but between 9.8 and 11.1 grams methane meter squared per year are produced at that site. And I'm sure the figure is between the 9.8 and the 11.1, or 6 and maybe 14 maximally. Right, so here's the global estimate. I know what I'll do. I'll have a look at the pixels. Now, what they've done here is they've taken Skiamaki or satellite data and combined it with a model for effectively groundwater table, or the depth of the water table, which is critical for driving methane fluxes because methane is produced anaerobically. So what they've done was calculated on a 3x3 grid the water table of the world. There we are. That's a UK, so that's the official water table for Scotland and England. You may be surprised to see that we have a higher water table. I couldn't believe it. But these are the documents which are currently being used by policymakers or whatever. And I don't know whether if it's just me that whenever I move in on my pixels, they're always so disastrously wrong. Right. Right, maps that do not convey the underlying uncertainties. I want them in room 101, and I want them in room 101 now. Now, one of the people that propagates these maps is him. And I was wondering whether or not I should put Peter Cox into room 101 or not. And actually, I'd kind of come to the balance that I wouldn't, because he's quite nice, actually, and good fun. But when I got the picture off the web and saw that moustache, moving on. I know, yeah. Oh, I think. So let's put the next object in room 101. Now this will hurt. I'm sorry about this, and it's going to hurt me as well a little bit, not a lot. Is we get these cover box measurements by using this kind. This is now technology. We have people. We put these boxes out on various experimental plots and measure the trace gas fluxes. Somebody will go out once a week or once a fortnight with a collection of several hundred syringes, and on average, the number of accidents they've had with this work is for every 900 injections, they get one through the finger. So people going out in this labor-intensive business collecting trace gas fluxes in this primitive fashion. It's just unbelievable. And we have real gaps in the technology. we've said before, we've got satellites that can give us the Skiamaki can give us the methane air concentration, and we have these boxes, these manual cover boxes, and they all work at different scales, and they have therefore different resolution, and they also work at different temporal frequencies. And unfortunately, a lot of the trace gas fluxes, particularly things like methane and nitrous oxide, they have a very high spatial heterogeneity and high temporal heterogeneity. So they're difficult to capture. We don't have the right technology for catching at high frequency over reasonable sized areas. When people have attempted this is a paper by Master Panoff, a beautiful paper, because he realized that nobody had been measuring methane out in tundra regions outside the comfortable periods of time. So he actually took automatic cover boxes and put them out there and discovered that a heck of a lot of the flux, now these are just histograms from the various cover boxes, he discovered enormous fluxes after everybody had left, basically. So that our estimates for methane fluxes from these systems are really dodgy because people haven't been measuring at the right times of year. And so we need to revise the estimates. One way of doing this is to use things like eddy systems. Currently, we're involved in looking at greenhouse gas balances for various energy crops, including miscanthus, the elephant grass, and willows, and so forth. And this was one of those occasions when I got into the pickup in the morning. It was pouring with rain. It was cold. We were expecting that it might be snowing, and we had to put field equipment out. And on the radio, Radio 4, came this voice called Sir David King, and he said, we really do not know whether we should be investing in energy crops in the UK because ultimately it's all about that greenhouse gas balance and we don't have the numbers. And I went, yes, because there I was suffering in the interests of my science to get those numbers because we don't have them. We don't have the measurements. In fact, something like N2O, we realize, could be a deal breaker for these crops. Because if you switch over to an energy crop and you stop putting nitrogen onto arable land, for example, suddenly your N2O fluxes go down and you've really got a win situation. However, we occasionally find major N2O fluxes from things like miscanthus and willow. There's an even worse problem that I didn't realize until a couple of weeks ago, is that farmers who are growing the energy crops are going, ooh, we're not quite getting the textbook yields out of the willow. Now, what we'll do is we'll put some nitrogen down to increase the growth of the willow. And if they put nitrogen fertilizer down, they're going to be emitting N2O. But that's not in their lexicon of interests. They just want to they know if they put 5 pounds down and get 20 pounds back of crop, they'll put the nitrogen down, regardless, really, of the ultimate objective, which is to prevent emissions or reduce the atmospheric burden of greenhouse gases. So unless you've got that interaction with the people who are doing this and they know why it's happening and they can understand the reasoning, unless that communication is clear, then you can have all kinds of blunders. And we have, this is wonderful. Somebody, who was it that said, these pieces of kit, scientists just want their pieces of kit to go, yes, we do. We have a device here, the only one in the world, that every second can tell us the N2O concentration at very high accuracy and the isotopicness. That's the 15N ratio of the nitrogen molecules and the 18O ratio of the oxygen molecules, which can go a long way to telling us the process that's giving rise to the gas. So the technology is just moving amazingly quickly. You don't get much for £10,000. That's a sort of plug at NERC, really. So we move forward from that. One of these chambers, this automatic chamber here, which actually I've modified from the sort of commercial one, is worth £3,500. So you pay £3,500 from Lycor, from the United States of America, for one chamber. We have 20, 30 chambers at a site, so it's very, very expensive. So we've actually been working on a much more inexpensive system for actually being able to take, is that a train or an object? Oh, good. There's a big for objection. So we have developed these linear systems where we can actually set up a couple of beams and then run one chamber system across, and therefore get lots of replicate measurements on different treatments and so forth. And we can build one of those for the same price as one of these automatic chambers. So there's a real technological development here. And the data we get are just as good. In fact, we've compared them with data that we get from other automatic systems. And that's sort of moved on a phase now to something that we're building down at Hes East, which is a three-dimensional sky gas system, which is a way of putting chambers down into an arena, in a three-dimensional arena, and measuring trace gas fluxes either on land or on water. Also, we realize that we can actually equip this with cameras or a variety of other instruments so that we can actually take measurements in the field in an automatic way. Multispectral scanners, etc. That's the Hes East campus from the air. It's a bit more complete than that now. And we're building... The sky gas system is going at the south end of that lake, and we're trialing it and prototyping it here. So what am I going to put in room 101 this time? Well, I'll show you what I'm going to put here. And this will hurt. We have used sophisticated engineering and technologies for quite a while in ecology for experimental manipulations. You know, the first excitement of seeing a phase system or opening and closing chambers, droughting systems, electronically driven and operating day and night in the field under our command, raising temperatures by 3 degrees in a feedback type way. So we're used to this, but really from the point of view of automating our experimental manipulations. I don't know who he is. You do. He's going into room 101. Oh. Yeah. He's not here, is he? He should. 100 years ago, I guess ecologists were using quadrats. 100 years ago, and now we still have people. Now, it's a great bonding experience, a great social experience. It's a good time to be had if the weather's okay. But really, come on. Similarly, all these types of measurement that we've been doing in these sort of very laborious, manual-intensive ways, and it's got to go. We have to develop automatic and more up-to-date ways of measuring these things that we've been measuring all this time. Why on earth are we still living in the Dark Ages? I don't know. Whew. Right. There is another one. I better be careful here. Multidisciplinary, interdisciplinary science. I think it's absolutely essential, but what is the role of the scientist in this? Is it really to be getting involved in politics? Is it really to be engaging with social sciences? What should we be doing? Now, I've often wondered, this is a classic slide of Watson and Crick. There's a piece of paper stuck on the wall behind their double helix. You're all familiar with this. This probably one of the most amazing discoveries ever made by human beings. These two, no wonder they're smiling. So using retort stands and different coloured balls, etc., they have constructed a molecule of DNA. I've used my own proprietary image enhancement software to see what it said on the wall. And it's their pathways to impact path. And their second one, I felt, was ambitious. Unraveling the secret of life. Come on. Creating a new form of coffee table decoration. I could live with it. And the crystallography was, it was quite interesting, I suppose, for chemists. What did they... Whoa! Come back. What did they actually discover? Oh. They were able to resolve contestant parentages because of their work. We could identify criminals. We can find horse meat in our beef burgers. We can develop transgenic crops. We can predict cancers. We can identify the bacteria on the teeth of dead nuns. We can build, Matt Collins, a time machine, and we can quantify the loss of our genetic library. All through these guys who probably didn't even have an impact plan. Well, well, well. I have spent some time working with one particular social scientist, trying to understand, first of all, the jargon and the words. And at first, it almost led to fights, because he would use words in a way that I was using my common lexicon, and he was using his precision lexicon. The same word would mean totally different things. And we realized that the objectives and things that scientists want to do and the things that policymakers want to do are very different. A scientist wants increasing scientific rigor. He wants replicates. He wants to demonstrate with a p less than 0.05. He wants to have experiments that he doesn't necessarily have many of them. He just has a few of them. The policymaker wants one demonstration plot, please, or a couple of demonstration plots where you've done this or you haven't done that, which doesn't have the same scientific rigor. So there's this tension between what we as scientists want and what policymakers want, which is a very difficult one to resolve. The other thing about working with the social scientists, when I said, well, we need to be consulting with the community of end users, etc. So let's have a town meeting. And he looked at me, and it was though I could have been threatening to kill his cat or something, because he said, what do you mean have a town meeting? I said, well, get everybody together and we all discuss the science, etc. That's the last thing you want to do, Phil. I said, well, what do you mean? He said, don't you know anything about social science? He said, you get the various interest groups together, you have focus meetings, you get their concerted opinion, and then you bring them together. You don't have town meetings. Was it last week, the week before, a water town meeting organised by NERC? We're scientists, or I'm a scientist. I'm not really trained as a social scientist. I haven't got a clue. They're professionals. I don't want to go meddling there. I would get very upset if they come and start formulating hypotheses and testing them for me. So there's a very different discipline there, and it is a skill and a whole toolkit of skills that we can't really just dabble in and out of. So now, I'd like you. Now, let's have a vote. Are we going to put pathways to impact? Imagine the next grant application that you wrote, you didn't have to fill in a pathways to impact, right? Would you want the pathways to impact to go into room 101 or not? Who wants it in room 101?
Well, I'm not taking names.
Yeah, well, yeah. You're only allowed one hand each. After this conference, no, I can't do it. I can't do it because we can't put it into room 101 because we've got to connect somehow, and it hurts. It hurts to write pathways to impact. You know, it really does. But I think we've got to be stretching in that direction. I'm very tempted to put it in room 101, but I don't think I can. Not after what we've heard here over the last couple of days. In fact, I've got an alternative. The sky gas system that we're building requires the expertise of physicists, in fact, aeronautical physicists to have the flight control systems, chemists, the equipment that we use to monitor what's going on, the environment department and the biology department, working together to create this thing, which is a very tangible piece of experimental kit. And what I'm doing is, instead of putting it into room 101, I'm putting it into room Yessie. And I'm hoping that that's the exact opposite of locking it away and never seeing it again. I hope that that's a way of actually incubating it and growing it and developing it. So that's where I see Yessie. And I'm looking forward to working with you, Sue, and with other people in Yessie. So congratulations on the birth of this thing, which is a very tangible piece of experimental kit. And what I'm doing is, instead of putting it into room 101, I'm putting it into room Yessie. And I'm hoping that that's the exact opposite of locking it away and never seeing it again. I hope that that's a way of actually incubating it and growing it and developing it. So that's where I see Yessie. And I'm looking forward to working with you, Sue, and with other people in Yessie. So congratulations on the birth.